So just a little bit about myself. I'm an applied mathematician and mostly working on artificial intelligence and, well, to be more precise, I'm a computational mathematician. And as we discussed in the breakfast, that there is a chain of hierarchy in mathematics where the pure math is on the top, and then it's applied math, and then it's a computational math, and computer science, and AI. But what I'm trying to talk about today, and hopefully can convince some of you, is that it's not really a chain, it's actually a loop, where maybe pure math dominates applied math dominates computational math, but computational math and AI may dominate pure mathematics in the future. Okay, so this is the plan of my talk. I'll talk a little bit about the background and the progress in AI for mathematics, and then what's our plan of how to achieve what I just described. So let me start briefly with a little bit historical review on the entanglement between AI and mathematics. And we know that the term of AI started in 1956 in the Dartmouth meeting. And if you look at the 10 of the major organizers of the meeting, 6 of them either having PhD degree in mathematics or they're mathematicians themselves. For example, like Shannon and McCarthy. At the time, he's assistant professor in the Department of Mathematics at Dartmouth College. And well, there are some ups and downs in the development of AI, and the recent renaissance of AI has largely due to according to this book by the two computer scientists Russell and Novick, by the victory of the needs over the scruffy. So what is the needs and what is the scruffy? The needs are those who believe that AI should be based on mathematical rigor, and the scruffy are those who prefer to try diverse algorithms and methods, extensive, hand coding and incremental testing. Does it sound familiar? Well, there's no such thing that one is superior than the other. Both are very, very important. It's just the state at that time. And along with the rise of deep learning around 2012 and more recently foundation model in 2021, the state has changed dramatically. The need faces challenges, and the scruffy gains momentum. And the division between theory and the practice increasingly with it. And as applied and composition mathematician, I feel this personally. In the past, we, especially during the 90s, from the 90s to 2010, before deep learning, the major breakthrough in computer vision and also in computational mathematics are like variational models, PDEs, wavelets, and computer sensing. And during those times, theory is actually ahead of engineering, where a lot of engineers, computer scientists, they actually read theoretical papers, they write theoretical papers themselves, and to gain intuitions to guide them to design better algorithms. But now it's actually changed dramatically, where engineering is far more advanced than theoretical research, which is currently the state, and the gap between theory and applications has been widened, at least for the past decade. And however, on the other hand, the further advancement of AI faces challenges as well. So, for example, GPT-4, even though it passes all the exams like we have seen in the morning, but it's still relatively weak in reasoning, and it makes ridiculous mistakes in terms of reasoning, and also Sora violates physics, like this video, what this video shows. And also, there are different aspects of AI research that die in need of theoretical guidance. For example, what's the better architecture so that we have better scaling law? Okay, so what is how should we improve the quality of the data? How should we collect, prepare, and generate better data so that we have better scaling law? And how do we actually train them, and how do we understand how the artificial brain actually thinks when it makes a decision, and how to make it safe? So we can rely on empirical studies, but it's very, very expensive to do all that, especially when you have a model that has trillions of parameters. Okay, it's not doable, not even for big tech companies. So we really need theoretical guidance. So now we're in a dilemma, right? So on one hand, engineering, and empirical studies has been way advanced, and the theory is, it's very difficult to keep up. On the other hand, we really need theory. So, what should we do? Well, that means, mathematicians, statisticians, and also theoretical computer scientists, what should we do? There was a very interesting discussion, online discussion by the community of statisticians. They talk about, what's the future of statistics, and how should they co-live with AI. The current state is that statisticians the character of statisticians, has been, attacked heavily by the AI community. And the very famous statistician David Dong's had this comment in his speech. He said that let's wait it out. He thinks soon the scaling law will hit the limit, which I personally don't agree with that, right? Because scaling law depends on a lot of things. You change the artifact, you change the quality of data, you change the way you're training your model, they all change the scaling law. We're seeking better scaling laws. It's not a scaling when the scaling law will hit the limit, because the scaling law itself changes. So then I thought, well, maybe we can be more proactive, right? Rather than just wait it out, waiting, engineering, hit the limit, waiting to be stationary, and then theory would actually come up. We could actually, evolve, improve together with the evolvement of AI. So I draw this chart. From left to right, it's AI for mathematics. From right to left is math for AI. And we all know what's math for AI, right? So we use mathematics, we all use mathematical knowledge to design better models, to design better algorithms. But there are more to this, right? So later I'm going to show you that we can also rely on our knowledge of mathematics to create high quality data, to train AI to get better in terms of reasoning. And on the other hand, that AI can actually help mathematicians to do research, can help us to understand mathematics better, to understand mathematics as a whole, and to help us to innovate in mathematical research. So before I dive into more details, maybe we should first ask ourselves, so what can AI do for mathematics? Do mathematics really need AI for help? Well, the answer is obviously yes, in my opinion. And I think the key is this word, efficiency. Improving efficiency in mathematics is actually the key in not just mathematical research, but also in all kinds of research. If you look at the paradigm shift in different fields caused by AI, is because AI has significantly improved the efficiency of their research. Right? For example, the AlphaFold family. Okay. So what about mathematics? So what kind of efficiency that we actually need in mathematics? So for a regular mathematician, especially a pure mathematician, we spend a lot of time generating proof and verifying our proofs and verifying other proofs. And humans make mistakes. So even though we may think that mathematics is a very rigorous a science, it's a formal science, very rigorous science, but natural language mathematics, or sometimes we call informal mathematics, it's not 100% correct. Even for the greatest mathematician like Terry-Tao, it's still not probability 0 that he will make a mistake, even though this probability could be very, 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 very low. Okay, and mathematicians make mistakes all the time, and sometimes an error in a paper, a mistake in the proof, may be found decades after the publication of the paper, and that make a lot of mathematicians wonder that, well, maybe the mathematical umpire has a lot of holes in it, and we just don't realize it yet. And that will actually make math, supposed to be a very rigorous science, to be shaky. Okay, so some people would worry the foundation of mathematics, and this AI can actually help. I will elaborate that later in my talk. And also, we all say that we're standing on the shoulder of our predecessors, of all the giants. But do we actually know where exactly is that shoulder? So it's quite often that one of my students would come to my office and say, "Hey, I have some new ideas," and they describe to me, and I thought, "Oh, okay, and then I said, "Oh, that's very interesting." And then the student will ask me, "Is this new? Has anyone done it before?" Who would know? We would never know. We just do Google search, we just search online, we couldn't find any, but that does not mean it's absolutely no. It happens to great mathematicians as well. It happened to my PhD advisor, where he trying to sell one of his great algorithms, and afterwards people, after 10 years, people in optimization community told him that, well, this algorithm has already existed in the literature since the 70s. He was quite upset. This is very often. So actually, Terry he has this challenge to AI, is that whether AI can help us quickly find that whether theorem is really new. No one has really ever thought about it in whatever forms of the theorem, and that will actually save us a lot of time. Because I think the fact is, if you look at the literature of the published papers, there are a lot of repeated ideas, and can we actually improve on that? And the third part is, as an applied mathematician, I encountered this trouble very often. So when I first started, studying deep learning, and I thought, maybe we could use optimal control theory to really understand it. But I know very superficial of optimal control, so I spent almost a year studying optimal control, all kinds of aspects of that, and then we couldn't get much, interesting result out of it. Well, maybe optimal control, and then later we realized that optimal control is too ideal, and it does not really, it's not flexible enough. But it took us a year to realize that. So can we actually reduce that 1 year of learning the mathematics subject and trying to find out whether that can really help us to solve the problem we have in hand? Can we reduce that to just a month, maybe a week? Okay, and then this is also related to the topic that we discussed in the morning. This is actually learning, and when I interact with GPT-4 after it first came out, I learned a lot. Not only a lot, it actually guided me in my own research. One of the architecture that I'm going to show you for a foundation model is actually inspired. It's actually suggested by one of the early version of Cloud. Okay, all right. So efficiently use of existing tools. That's very, very important, because it took us a long time to learn a complex mathematical tools, but with the aid of AI, you can significantly reduce that time. Okay, and there are more examples. So efficiency is actually the key, right? And if you look at all the other subjects, I think mathematics maybe is one of the very few subjects where we're not taking enough advantage of technological advancement. But we have good excuse, right? If we want to have a tool that can actually help us to do our daily research, we really need AI to be strong enough. But AI in the past, I think it was an insult to our intelligence. But now I think it's different. So what's the main theme of AI for mathematics? It's search and retrieval, autoformalism. I'll show you what does it mean by autoformalism, theorem proving, and a counter example generation, and all that. So we need to develop AI models to help us to expedite all of those, so that we can actually focus on the real innovation thoughts, and use AI to help us to actually polish the thought and to develop the thought to do something that really matters. Okay, so now let me just do a little quick literature review and how people actually use AI to improve, to help with mathematical research. And I think the most well-known work, it's also a fairly recent work, is done by DeepMind and Jordan Williamson. Jordan Williamson is he's an Australian mathematician. It's a very famous mathematician as well. He gave his plenary speech in 2018 at ICM. And if you ignore the blue boxes, and that's a normal mathematician. That's how mathematicians usually do mathematical research, right? The person would have a hypothesis that, well, maybe X and Y, a set of invariances, for example, may have a neat, interpretable, and beautiful relationship. And he or she will make a conjecture and try to prove that. And if he or she cannot prove that, they will adjust the conjecture and then just repeat it again. Okay? And this could take months, years, or maybe decades. The blue boxes is where AI can actually expedite this process. So let's say that the dependence between X and Y may be very convoluted, but we can actually generate a lot of data and train a machine learning model. And we can interrogate that trained machine learning model to acquire some intuitions to help the mathematicians to craft a more a plausible conjectures, right? Rather than blindly search in a very large space, you can just significantly reduce that that space of possible conjectures and possibly to be converted into a valid theorem and valid and meaningful theorem. Okay, and they actually did. Using this approach, generate two new and interesting theorems, one in topology and the other one is in combinatorics. All right, and this is actually done by me and another colleague of mine. He's a pure mathematician, I'm an applied mathematician. We read the paper by DeepMind and thought, okay, maybe we could choose try something on my colleague Xu He. His research is on affine the linguistic variety, and whatever that means. I don't understand that, but I know it's a set, and he wanted to know the dimension of this set. So we designed. It's a very similar pipeline, but we did some tweaks on that, and we quickly rediscovered a theorem that they have discovered in the past decade, and more interesting, we actually inspired them to craft a new theorem, which is the second box on the corner right. And also we found a lot of interesting intuitions where my colleagues couldn't think of a way to use them to craft a conjecture, but we all record that in our paper. Okay. So if you're interested, you can look into the details, and the paper has already been published. Okay, so this is a very interesting, a new way of guiding human intuitions using machine learning models. The upside is that you do not really need to have a lot of computes. The downside is you really need to pick the right problem to work with, because this approach does not really apply to, it only applies to a very limited set of problems, and actually heavily rely on human intuitions. And we know that sometimes human intuitions takes time, so it does not really solve the efficiency problem. And the other approach, I think it's more systematic, which is through the training of a large language model through this circle, but we want to have this circle in the domain of mathematics rather than the generic domain. However, data in mathematics, especially high quality data in mathematics, is seriously lacking, and actually because of that, there is an AIMO, another Math Olympic competition. It's organized concurrent with the human IMO competition, but it's AIMO, and we and a couple of companies and the university, we actually came up, and we actually got the first place. We scored. We got 29 out of 50 problems correct, and more importantly, we actually created a very high quality math competition level data set. So we were actually very happy, but we were only happy for a few days until alpha proof came out. Okay, and then we back to anxiety. All right. So this is the issue of AI, because it developed so quickly, and this big tech companies, they also doing AI for mathematics with no reason, because I don't see any profit of doing such things, but they do it anyways. Okay. But anyway, in general, the reasoning ability of AI is still lacking. If you look at the reasoning abilities in terms of multitask reasoning and also coding, mathematics is still their weakest weakest facet, and the reason is lack of high quality data set. So what could be a high quality data set for mathematical reasoning? So I think it's through the mathematical formalism. So what is the mathematical formalism? This is GB4's answer. It's actually it's not a natural language. It's not mathematics written in natural language, not written in LaTeX. It's actually written in a computer language, and you can actually compile that written proof. I'm going to show you an example later on. And if it passes the compilation, that means the proof is correct. If it does not pass, that means the proof is wrong. Okay, so it's just it's 100% guaranteed whether it's correct or incorrect. And conversion from informal math, which is written in natural language, to a formal mathematics. We could have different formal verification systems, but it's a computer language. This conversion, this translation, it's more complex than simple translation among different languages. But this translation is what we call digitalization, right? Because after you convert it into a formal system, and then you can verify almost in real time whether a proof is correct or not. While in natural language, we need to rely on human assessment, which could take time, and it's not 100% guaranteed to be verifiable. Okay, And right now, the proof assistant, the most popular proof assistant is called Lean, which is developed by Microsoft in 2013. And this is actually a written proof of the composition of two continuous functions is still continuous in terms of topological language, but it's in Lean. And if you look at it, it's it's some kind of computer program. But if you compile it and it's passing compilation, that means it's actually correct. And this is not just a toy, right? The major league mathematicians also use that to verify their proofs. For example, Peter Schoza, which is he's a physics medalist, which is he used this Lean at the help of the Lean community to verify, well, according to his own words, one of his most significant theorems. Right? And also Terutal, he also used it to verify one of his proofs on a conjecture. And also, there is a library in Lean, written in the language of Lean, of mathematics, which has a good coverage of college level and also sort of research level mathematics, especially in algebra. Okay, and it's relatively weak in other areas. And it, earlier this year, about 6 months ago, I checked. It has 140K theorems and 70,000 definitions. Okay. However, to do this translations by human, that is, you need to learn a new language, and you need to learn how to translate natural language proofs, statement proofs, to formal statement proofs. The learning curve could be very steep. Well, this is the feeling, from Terutal after learning the language of Lean. It's actually he found that there's a steep learning curve, and also doing formal math can be very slow. Okay, much slower, 25 times for him slower than doing informal mathematics, and it's about 100 times slower for our students to do mathematical proofs in Lean compared to in natural language. Okay, so actually that leads to what we're actually planning on doing. This is a big project back at Peking University, and I'm going to show. Well, I call it PKU, Peking University AI for Math team, and I'm going to show you what we're going to. What we are doing and what is our current progress, and you're all welcome to actually join us in this big project. So first of all, what do I mean by high quality data? Okay, so a high quality data should have its formal part and also its informal counterpart, and also we need to have a stepwise evaluation of that. Right, this is very important, and so it's basically a reward system. And after you have let's say that we have convert most of mathematics, or let's say just all mathematics, because theoretically we can convert all mathematics into Lean, 100%. Okay, after you have converted, you literally making mathematical proof a game. You can create a simulator that can simulate any mathematical reasoning in the simulator, and also you can immediately check whether the proof is correct or not. Okay, so you can actually convert mathematical proof into a game, and it is some kind of Markov decision process, and you can use reinforcement learning to actually train an AI that can master all the proofs of theorems at the same time. Okay, so this is just ideally speaking. Okay, actually I had this idea about a year ago, and very recently I found that it's pretty much DeepMind has taken the very same strategy. It makes me both happy and nervous. Okay, I'm happy because it's a correct way, and at least DeepMind also pick it up. We're nervous because DeepMind pick it up, and we're having a very big high-tech company as a competitor. And for AlphaProof, there was rumor has it that they have spent about $50 million to $200 million US to train AlphaProof, where we don't have that kind of money. If I had that kind of money, I'll retire. Okay. All right, but anyway, so we after we have read that we read that their blog, and then we adjust our strategy to make it a little bit different from DeepMind in order to actually succeed to a certain extent. Okay, so we have a very multidisciplinary, but within mathematics, a research team. We have pure mathematicians, applied mathematicians, and also engineers, computer science working very closely together. And we're investing a lot of our effort to create a high-quality mathematics data set, as I described earlier on, according to the quality definition. And also we're building an AI toolkit. In particular, we're building two foundation models. My team, we're building two foundation models. One is the foundation model for reasoning. We're hoping to have one model that can prove all theorems. If you have one model that can prove all theorems, it must understand mathematics as a whole. We really need a model, an AI model that can understand mathematics as a whole, so it can actually teach us to master the tools of all mathematics, and so that it will actually help us to solve problems in hand. For example, maybe we can easily understand to give a better mathematical foundation of large foundation models. Okay, and also a foundation model for computations. In particular, we're trying to train one AI model that can solve all PDEs, at least all PDEs in the continuum mechanics. Okay, in the micro scale. And also, with all that, we're building a co-pilot. I call it ReasLab, which is short for Reasoning Laboratory, and so that it actually will help us help mathematicians to do research and also for educations. So later I'm going to show you some of the partial results that we have got. The first set of results is on how actually we can build AI models to assist mathematicians to do this formalism. Okay, and we call it auto-formalism or interactive auto-formalism. Is because purely rely on human, it's very, very slow. We want to expedite this process by building models. So the first model that we built is to help mathematicians to quickly search the gigantic and it's also growing lean data set called Mathlib4, and we call it lean search tool.
We're introducing ReasLab Smart Search, an AI-powered tool to find theorems in Mathlib4. Let's start with the informal search mode. Imagine you're looking for Bazal's theorem. With ReasLab Smart Search, simply type your query in natural language and instantly access a curated list of relevant theorems from the informalized Mathlib4 corpus. But what if your query doesn't yield the expected results? Take, for instance, searching for Wedderburn's little theorem. A direct search might fall short due to the varied ways theorems are formulated in the database. This is where our query augmentation feature comes into play. With a single click, our GPT-4 powered augmentation transforms your initial query into one that's more aligned with the language of our corpus. For instance, it might expand Wedderburn's little theorem into a more detailed statement, such as every finite division ring is commutative, enabling our search engine to identify the corresponding theorem in Mathlib4. A finite integral domain is a field. Empirical evidence from our benchmark testing shows that the query augmentation feature boosts the recall of our system by an impressive 8%. Moving beyond the informal search, we offer an equally powerful formal search mode. This mode is designed for those who prefer the precision of formal math. For example, when exploring theorems related to matrixed debt, our tool efficiently displays a wide range of relevant theorems, covering topics such as the determinant of a 2x2 matrix, the determinant of a family of vectors with respect to some basis, and the determinant of a block matrix. This feature is particularly useful for experts in formal math, allowing for a more targeted search experience.
Okay, so this is machine learning. This is called semantic search, but we're doing semantic search within the Mathlib4, and now we're doing we're working on building a semantic search engine, to include natural language mathematics as well. And very recently, I heard that Terry Tao himself, he's also raising money to do the same thing. We like to have some competitions. So after we have released this tool to the biggest community in Lean called Zulip, we get a lot of positive feedbacks. And also, we have released our API, and someone has already integrated into VS Code. So people actually like it. But this is actually just semantic search. We still need, people still need to browse through the search results and just put together with the code, and it still needs a lot of human touch. So very recently, we just submitted a paper to iClear this year. To auto-formalize statements and also rely on large language model to do some ATP as well. So mostly auto-formalism of the of statement. The current challenge of doing auto-formalism, even just for the statement, is that the lack of high quality data sets. So this is the first thing that we did, is that we created, and also open source, a very high quality data set. We call it Herald. And also the model is also called Herald. And we built a pipeline to produce, not to process the existing data, and also to augment, to generate more high quality data, doing all kinds of data generations, using knowledge of mathematics. So we have two pipelines. The one is to generate the data, and the second one is to the deployment of it, to do auto formulating, to do the translation from natural language math to formal language math. And because of this, we have significantly augmented that it's a data set with almost 1 million natural language and formal language and NLFL pairs, and it's the quality significantly surpassed the existing benchmark. Okay, so that also means that data is actually much more important than the model and the algorithm, at least at the current stage. And also the knowledge in mathematics is actually built in, not in the model or in the training, it's also in the data. The data, the cleanup of data and the augmentation of data, it actually requires a lot of understanding of mathematics itself. Okay, and also recently we actually used this to apply them on some real tasks. There is a project called Stack Project, which is an algebraic geometry project. They have a lot of theorems and exercises with proofs, and it's only very small percentage has been formalized. We actually apply this to one of these subsections, and the results are pretty good. So human can just after the translation, human can just need to modify a few things, and then it's already directly applicable. Okay. So actually, we're same as lean search, the semantic search. We're going to create a cloud version of service so that everybody can actually use this. Okay. So this is more on how to quickly generate a high quality data set so that we can actually train a model that can do reasoning better. This is on competitions. So we built a very specific architecture, and we're hoping this model can solve all PDEs, these all PDEs in continuum mechanics. And like I said, that this particular architecture, the key of this architecture is how we actually encode the PDEs, the symbolic numerical encoding of PDE. The design is actually key, and this design is suggested by cloud. Okay, I just tell the cloud what is exactly what we need, and it gives us 4 suggestions, and he strongly recommended 2 of them, and then picking 1 of them. Okay, it's not like that we're not gonna stumble on this thought. Maybe after a few months of trial and error, we may end up with the same architect because it actually makes sense. But at the aid of AI, we can significantly reduce that time. So this is why I said it improves efficiency. Okay, and we have a 1D version already released, and we have a huge data set with 3 million PDE and its solution pairs. And the paper and also the data set and model we've made public available. And in less than a month, we're going to release our 2D version. It's supposed to be a GIF, but doesn't matter. Okay, so this is a 2D version. And more interestingly, so this is supervised learning. We generate the data relying on traditional solvers. And traditional solvers fail for a lot of cases. And we just pick the cases where the traditional solvers succeed and train the foundation model, train the PD former, and then we go back. We use the foundation trained foundation model to test them on the cases where the traditional solver fails, and you can see that the foundation model succeeded where the traditional solver fails. So it actually perfectly interpolates among the data, among the good quality data, and it actually surpasses at least some of the models in terms of the flexibility and the coverage of the PDs that the model can solve, which is what I personally think is a very interesting aspect of it. Okay, so what's the near future? I think what we're trying to build is that we're building an AI assistant that can help us, can support, in terms of reasoning and also computations, and will help us to expedite our research and also to help us in terms of education. Actually, we have recently released a university-level AI for education system at Peking University. In Chinese, we call it 问学, which means learning through asking questions. Okay, that's the that's the key part of the system. We're trying to encourage the students to ask questions so that they can learn better through this interaction in this interactive way. But for some subjects it does pretty well, but for mathematics it's still lacking because the foundation model itself is not that reliable in terms of reasoning. But for other subjects, for healthcare, for literature, for some engineering and economy, and I think that's pretty good. Okay, but you do need, as I think as discussed earlier in this panel, we do spend a lot of time training our faculties and also giving a lot of examples on how to do good prompt engineering, and also we write a paper on the mathematics frameworks for prompt engineering. It's optimal control problem. Okay. But anyway, so let's come back to the loop, right? So instead of having only the traditional way of math for AI, which is using mathematics to design better models and algorithms, we can also provide AI with high quality data so that we can improve AI in terms of reasoning. And as a return, AI can help us to understand mathematics as a whole, to help us to expedite mathematical research, and also to help us better to train our students. And then this loop can actually go on. So I think this is really a mutual beneficial research. It's not just math help with AI or AI help with mathematics. It has to be a circle. So that's why I said that this chain of hierarchy is not really a chain. I think it's a loop, right? It's well, in Chinese we said that 一物降一物. That means everything has its has something that can dominate you. Even for pure math, I think AI will actually change the way we do pure mathematics. Well, hopefully in the next few years we're going to see something happens. And with that, I conclude my talk, and thanks for your attention.